In our last module, we have discussed pointwise convergence of sequence of functions and also seen some examples on deciding the limits and pointwise convergence, how to decide the pointwise convergence, and given some examples. In this module, we shall discuss another mode of convergence of sequence of functions, which is known as uniform convergence. Actually, uniformity means for every x the convergence holds. So, in this module we shall define uniform convergence, give some examples using the first principle or the definition, and then provide a necessary and sufficient condition for checking uniform convergence. We also discuss the definition with some examples and give necessary illustrations for the uniform convergence. However, the most important thing with uniform convergence is that it enables us to interchange some operations, some mathematical operations. For example, we can interchange the operations of limits, one taken over x and the another taken over n. So, we can exchange this. We can also exchange differentiation and limit, that is we can interchange limit as n tends to infinity with the derivative sign of f n x with respect to x. And finally, we also see that uniform convergence enables one to take the limit inside an integral. So, this is all about this module. So, we have just seen what is pointwise convergence, and we have also seen some examples. It is seen that for pointwise convergence, it is necessary to get a feasible choice of nu x epsilon, so that the question is natural whether we can find a nu dash depending only on epsilon such that the convergence holds. So, in a way, we want to know whether we can find some n independent of x retaining the property of convergence. So, this leads to the concept of uniform convergence. So, let us consider some examples. So, first of all, consider the sequence of functions x to the power n divided by n square for x belonging to open interval minus 1 plus 1, and we have already seen that f n x tends to 0 pointwise on the open interval minus 1 plus 1. Now, one can recall that for the above example, we get a choice nu x epsilon which equals box of 1 by square root of epsilon plus 1. Naturally, such a choice is independent of x, thus we get a common value of nu x epsilon, ensuring pointwise convergence, or in other words, we get a range of values of n which is independent of x. Therefore, the convergence in this case is more than pointwise and termed uniform in the sense that a uniform choice of nu x epsilon exists, that is such a nu x epsilon is independent of any x. So, let us come to our formal definition of uniform convergence. Suppose f n x is a sequence of functions on A to R. F n x is said to converge uniformly on A, the set A, if for any given epsilon greater than 0 there exists an integer nu dash depending only on epsilon, such that for all x belonging to A and n greater than or equal to nu dash, the absolute value of f n x minus f x is less than epsilon is satisfied. One can use some symbol to indicate uniform convergence on A. Naturally, it is easy to observe that uniform convergence implies pointwise convergence, and uniform convergence on some set A implies that on some set B, where B is a subset of A. So, let us start some graphical illustration of uniform convergence. Suppose fnx is a sequence of functions on A to R such that fn converges uniformly on A. Then uniform convergence can be thought of the existence of some nu dash independent of x such that the graph of fn will lie inside the band f minus epsilon up to f plus epsilon for every n greater than or equal to nu dash. Actually, the existence of such a band can be seen from the definition of uniform convergence. So, the concept, the bands can be seen from the graph that there is some f plus f, the curve of f plus epsilon, and there is some curve of f minus epsilon, and as we increase n, we get all the curves are enclosed within this band. So, as earlier, we need some intuitive methods for checking uniform convergence. Suppose using some intuitive method, a limit function f is decided and pointwise convergence is established. Also suppose we get some nu x epsilon for epsilon greater than 0 and x belonging to A. So, consider 2 points A and B both belonging to the set A. Then for a given epsilon greater than 0, we get real numbers nu A epsilon and nu B epsilon such that the inequalities absolute value of fna minus fa less than epsilon and absolute value of fnb minus fb less than epsilon are both satisfied. Naturally, the first inequality is satisfied for every n greater than or equal to nu A epsilon, and the second inequality is satisfied for every n greater than or equal to nu B epsilon. So, both the inequalities will be satisfied if n greater than or equal to maximum of nu A epsilon and nu B epsilon. The above suggests that if a feasible nu dash epsilon which is defined as the supremum of nu x epsilon over the set B exists for some subset B below of A, then Fn might converge uniformly to B, to F on B. So, let us illustrate the concept using some examples. So, as earlier, consider the sequence of functions defined by x square by n for x belonging to the real line. Then as earlier, for fixed x, we find the limit as 0 for every x belonging to R, and we have determined nu x epsilon as box x square by epsilon plus 1. Naturally, the supremum value of nu x epsilon over the range over the whole real line is not finite, but for example, if we consider the supremum value over some subset say 0 to A, then we get the supremum value as absolute as the box of a square by epsilon plus 1, which is finite as long as A is finite. Therefore, Fn converges uniformly on the interval 0 to A, open interval 0 to A, whereas Fn converges to 0 pointwise for every x belonging to the real line. So, we find that pointwise convergence does not imply uniform convergence always, but the uniform convergence over 0 to A implies pointwise convergence of Fn to the same function over the same interval 0 A. Next, consider our old example where the sequence of function is defined as x to the power n for x belonging to open interval 0 1. Then using the methods previously discussed, we find that limit of fnx equal to fx pointwise on 0 1 for fx equal to 0 for all x belonging to open interval 0 1. Then as earlier we have derived nu x epsilon as a box of log epsilon divided by log x plus 1. However, limit of nu x epsilon as x tends to 1 minus is not finite, and hence the convergence cannot be uniform on open interval 0 1. However, mu x epsilon is an increasing function in x, and hence if we take some b belonging to the open interval 0 1, then supremum of mu x epsilon over the interval 0b, open interval 0b, is finite and is given by mu b epsilon. Therefore, the convergence is uniform over 0b where b is strictly less than 1. Consider our next example which involves the sequence of functions x to the power n by n square for x belonging to the open interval -1 to +1. We have already seen pointwise convergence to fx equal to 0 for all x belonging to real line, and we have also decided n or nu x epsilon as box of 1 by square root of epsilon plus 1. So in this case it is very clear that we automatically give some choice of nu x epsilon which is independent of x, and hence the convergence is uniform over the open interval -1 plus 1. Thus, we observe from the previous examples that pointwise convergence on A does not necessarily imply convergence, does not necessarily imply uniform convergence on A. Actually, in this example, we get pointwise and as well as uniform convergence over the same interval, but in the previous example we have seen pointwise convergence on a greater set and uniform convergence in a subset. So next, consider the sequence of functions nx divided by x plus n for positive x. It is already seen that the sequence of functions converges to x pointwise for all x greater than 0, and the corresponding choice for nu x epsilon comes out as box of epsilon divided by x square plus 1. In this case also, the limit of epsilon divided by x square as x tends to 0 plus does not exist, and hence convergence cannot be uniform over 0 infinity, the open interval 0 infinity. However, 1 by x square is a decreasing function, and hence supremum of nu x epsilon is finite for some x belonging to B, a subset B, where B can be taken as left closed right open interval AB with positive A. Hence, the convergence is uniform over AB for some positive A. In our next example, we consider the sequence of functions nx divided by x square plus n square for positive x. We have already seen that the pointwise limit is 0 on the interval 0 infinity, and we have also deduced the corresponding choice nu x epsilon as box of epsilon divided by x square plus 1. Then, just as in the previous example, it can be shown that convergence is uniform over AB for some positive A. Similarly, uniform convergence for the other examples as we have discussed in case of pointwise convergence can also be investigated. So far we have discussed uniform convergence from first principle, that is whether a maximum value of nu x epsilon exists or not, or if exists, on which interval it exists, and finding such an interval we have decided uniform convergence of the sequence of functions. So, but for some complicated examples we need some mathematical formulation so that one can check uniform convergence easily. So we need some simpler conditions. So suppose fnx is a sequence of functions on A to R which converges pointwise to some fx on A. Then fnx converges to fx pointwise on B which is a subset of A if and only if Mn which is defined as the supremum of absolute value of fnx minus fx where the range of supremum is x belonging to B tends to 0 as n tends to infinity. Thus, we get a simpler condition for uniform convergence. Actually, we are replacing our finding maximum by some sequence of n, and to check whether this goes to 0, and if it goes to 0, then we can say uniform convergence over the set B, and if it doesn't go to 0, uniform convergence cannot be decided. So let us discuss some consequences of uniform convergence. If fnx and gnx converge uniformly on A, then C multiplied by fnx also converges to Cfx uniformly on A, and if we consider the sum function, that is fnx plus gnx, then the sum function also converges to the fx plus gx on A, where fx is taken as the uniform convergent, the pointwise limit of fn, and gx is taken as the pointwise limit of gn. Now again, if fnx converges pointwise, fnx converges uniformly to fx, and gnx converges uniformly to gx on A, and there exists some quantity m which is positive, such that absolute value of fnx less than equal to m and absolute value of gnx is also less than equal to m, then the product function fnx multiplied by gnx also converges to fx gx uniformly on A. So let us consider some example of this. Consider first of all the sequence of functions given by nx multiplied by e to the power minus nx for x greater than equal to 0. We have already seen that fnx converges to 0 for x greater than equal to 0, but the mode of convergence was pointwise, and the mode of convergence was also uniform over some suitable interval. So let us consider our mathematical definition for illustration. So in this case, Mn is defined as supremum over the range x greater than equal to 0 of nx e to the power minus nx, and a simple algebra shows that nx multiplied by e to the power minus nx has a unique maximum at x equal to 1 by n, and thus Mn comes out as e to the power minus 1, which is non-zero and independent of n. Thus the convergence is not uniform over the 0 infinity set. However, if we consider a subset for subset 1 to infinity, then Mn tends to 0, and hence the convergence is uniform on B. Consider our next example, which is which involves the sequence of functions x to the power n for x belonging to 0, 1. We define fx as 0, that is the limit function, as 0 if 0 less than equal to x less than 1, and fx as 1 for x equal to 1. Naturally, the convergence holds trivially for x equal to 0 or 1. However, we have already seen that fnx converges to fx pointwise on x belonging to 0, 1 interval. Now Mn is defined as the supremum value of x to the power n for x in the range closed interval 0, 1. Since x to the power n is an increasing function, it has a unique maximum at x equal to 1, thus Mn equal to 1, which is different from 0, and hence the convergence is not uniform over the whole closed interval 0, 1. However, if we consider B as a subset of 0 to 1, that is, say, closed interval 0 to A, closed interval 0 to A for A strictly less than 1, then Mn tends to 0, and hence the convergence is uniform on B. Next, consider our already discussed example, that is fnx is the indicator of absolute value of x less than equal to n. It is already seen that the pointwise limit is 1 for every x. However, the absolute value of fnx minus fx comes out as indicator of absolute value of x exceeding n. Now for every n greater than equal to 1, indicator of absolute value of x greater than n is either 0 or 1. Thus in any case Mn equal to 1, which does not converge to 0, and hence the convergence is not uniform, though we have seen pointwise convergence for this example. So next, consider our next example where the sequence of function is defined as x square multiplied by e to the power minus nx for x belonging to 0, 1. It is easy to observe that fnx converges to fx pointwise on 0, 1 for the limit function fx equal to 0 for x belonging to closed interval 0, 1. Now, in this case the supremum value comes out can be calculated, and we find mn using the supremum value. Actually, a simple algebra shows that x square multiplied by e to the power minus nx has a unique maximum at x equal to 2 by n, and thus mn comes out as 4 by n square multiplied by e to the power minus 2, which goes to 0, and hence the convergence is not uniform over 0, 1. So let us consider some facts or some consequences of uniform convergence. The first one is involving uniform convergence and limit interchanging. If fnx converges to fx uniformly on A, where fn is continuous on A for every n, then f is also continuous on A. Thus, for any small a belonging to capital A, we have limit x tends to A, again limit n tends to infinity, fnx is the same as limit n tends to infinity then of limit x tends to A fnx. That is, the limit operations on x and n are interchangeable as a consequence of uniform convergence. So next, consider uniform convergence and differentiation. Suppose fnx is a sequence of functions on closed interval ab such that for some x naught belonging to open interval ab, fn x naught tends to fx naught, and fn dash x, that is the first derivative of fnx with respect to x, exists at all x belonging to closed interval ab and converges uniformly to some function g on closed interval ab. Then fnx converges uniformly to fx on closed interval ab, and gx is f dash x for all x belonging to closed interval ab, that is limit of the derivative of fnx is the same as the derivative of the limit of fnx for every x belonging to ab. That is, as a consequence of uniform convergence, differentiation and limit operations become interchangeable. Lastly, we discuss the exchangeability of integration and limit. Suppose fnx is a sequence of Riemann integrable functions on ab, that is closed interval ab, such that fnx converges uniformly on fx on ab, then f, the limit function, is also Riemann integrable on closed interval ab, and limit of the integral of fnx, the integral over the range a to b fnx dx, is the same as the integral over a to b of the limit function, that is limit n tends to infinity fnx dx. So lastly we find that as a consequence of uniform convergence, we can interchange the limits of limits on x and n, we can interchange differentiation and limit operators, and we can also interchange the integration and limit operators. So we have just seen how uniform convergence works, what are the consequences of uniform convergence, how to decide uniform convergence, and some necessary and sufficient conditions for checking uniform convergence. All these are illustrated using some examples. However, like our ordinary sequence and series, we can also have series of functions, that is a series which not only involves which also involves x. So such type of series are called series of functions, and there are some concepts of convergence and checking methods of convergence. So in our next module we shall discuss convergence of series of functions, and give some consequences of convergence in terms of exchange of operations like limit, differentiation and integration.